Welcome to our last week of unit number 5 modules. And so this is module number 30, and we're going to cover weak acids and what we call the acid dissociation constant. So we're going to calculate another K value, and this is going to be Ka as far as the A standing for acids. Okay, today's lesson is pretty much the same as Wednesday's module because Wednesday you're going to calculate Kb. Okay, so it's not too tricky for this lesson and Wednesday's lesson, and then we're going to put those two things together for Friday, and then we're going to be completely done unit number 5. All right, so this one may seem like it covers a lot of pages, but really there's only about 3 or 4 examples through the whole package because it's one of those practice and then the answer is given to you pages, so you really don't need a printer or anything for this lesson. You can just simply do a couple of the calculations and see if that makes sense, okay? So we're going to cover pages 35 to 44, and then in the review package, you're going to be able to calculate the answers for question 17 to number 20. So there's 4 questions to complete in the review package. Okay, so here we go. Weak acids and the dissociation constant. Remember, we're calculating a K value for only the acids that are weak, because if it was a strong acid, it would dissociate 100%, and then you would have an arrow that looks like that, and then it's not an equilibrium, and you're not calculating a constant for an equilibrium. Does that make sense? So we're not calculating anything for strong acids. We're only calculating a K value for weak acids because they dissociate less than 5%. Okay? So recall, a strong acid totally dissociates 100%, and the weak ones slightly dissociated, and that's typically less than or equal to 5%. Remember, if you were to draw what that ionic equation would look like for a strong acid like hydrochloric acid, you would be able to know the concentration of the hydrogen ions because it's a 1-to-1 ratio, and if you know what the concentration is for the hydrochloric acid, well, then you already know what the concentration is for the hydrogen ions. If you have a 0.15 molar solution of hydrochloric acid, well, then you know your concentration of your hydrogen ions is going to be the same. So those are easy. You can calculate the pH of those very easily. However, if we look at those acids that are weak, they are slightly dissociated, they set up an equilibrium, we can calculate that equilibrium constant at a particular temperature. So think about it this way. If you had a 0.15 molar solution of acetic acid, which you remember from your memorized list that that's a weak acid, you'll know that the hydrogen ion concentration is not going to be as much as 0.15 moles per liter, because only a small percentage of the acetic acids will actually dissociate and break apart. So if you set up your equilibrium expression to look like such, then your hydrogen ion concentration, you could figure that out if you knew the pH, because we just did our pH calculations in the last lesson, okay? You remember that your pH equals the negative log of the concentration of the hydrogen ions. So if you know what the pH is, you can calculate the hydrogen ion concentration, okay? So you can put that into your calculator and you're like, yeah, 1.6 times 10 to the negative 3 moles per liter. That's very small, isn't it, compared to the concentration of that weak acid that you've got. Could you calculate how much of it, the percentage that was dissociated? You could, right? You could calculate that if you knew what your answer was divided by the total number of acetic acid molecules you would have, and you've got 1.1%. So again, that just confirms that acetic acid is a weak acid, and you could simply put a pH meter in there or some pH paper, although it's not going to be as accurate as a pH meter would be. But you could get the pH, calculate your hydrogen ion concentration, and actually figure out how much actually was dissociated. Okay, so what's the expression look like? Well, it looks the same as every other single K value that we've been calculating. You take the concentration of your products over the concentration of your reactants. You include anything that's aqueous, anything that's a solid or a liquid you don't include. So it's just the gases and the aqueous. And what do we call that? You may see that equilibrium constant for acids be called the acid ionization constant. acid dissociation constant. There's a few different terms you could use for that. Okay, does that make sense? Remember that these are the concentrations at equilibrium because it's the equilibrium constant. It just happens to be for a weak acid because they are the ones that set up an equilibrium, again, because not very many of them dissociate. Okay? All right, so here we go. What does the question like that look like? Well, if you're given a molar concentration of acetic acid, and then you're given the pH. So what would that look like as far as an ice table? Initial concentration, change in concentration, equilibrium concentration. Okay, so you can see that you've got your 0.15 molar concentration here. That's what you've got initially. We certainly know that if you're starting with just the acetic acid, then your initial concentrations of your other two ions on the other side of the equilibrium sign are 0. You know these are going to go up and these are going to go down. So where does that pH value come in? Well, the pH value right here, the 2.79, is what you use to give you the equilibrium concentration of the hydrogen ions. Can you see that? Okay. Once I know that goes up by a factor of 0.0016, this is also going to be 0.0016. And my change in concentration of my acetic acid is going to go down by a factor of 0.0016. So I can calculate, because I know the pH, I can know the equilibrium concentration of the hydrogen ions, and now I have concentrations in that whole bottom row of my ice table. So what do we do with that? Okay, so once we've got that information, you can set up a K value. Your expression for the acid dissociation, you get a value. And again, just note that because of rounding and how they decide to do the rounding errors, you may get a bit of a different value if you're actually looking this up in the table. But always remember too that K varies with temperature. So that would be the Ka value at 25 degrees Celsius. Okay? All right, so here's the kinds of questions you're going to get then. So just based on that example, you're going to work through the next few pages. First example, calculate the Ka of a weak acid if you're given the pH. So what are we going to do again? Essentially, you're going to use the pH to calculate the hydrogen ion concentration. That'll be the concentration at equilibrium. And then you can figure out how much actually was dissociated. Okay, so that's your first example. And then remember, all the answers are here. So on page 37, you get another example. Do it one more time. Calculate the percent dissociation as well, because you'll be able to do that. Then you're going to go over again, and it's like now you're just going to reverse the type of question that you're given, because what if for this question you're given the Ka value, and now it says, well, what's the pH of that solution? Could you figure that out? You can, right? Because for a question like this, if you're given the Ka, well, then you're solving for the hydrogen ion concentration. And once you know the hydrogen ion concentration, that's your pH formula. pH equals the negative log of the concentration of your hydrogen ions. Okay, so there's not too much for this module at all. Keep on working away. You'll notice that there is a bit of an assumption example. Again, we can try that. And then another question on page 41. And you're going to keep working your way through using your ice tables, okay? Once you get to the bottom of page 44, you're done. For the calculating the Ka, and if you want to work ahead and you want to do what Wednesday's module is going to be looking at, it's essentially doing the same thing as Ka, but now you're going to calculate Kb for our weak bases. And then on Friday, we're going to put the Ka and the Kb together and see what we get. Okay, so hopefully that was helpful, and good luck with finishing up this week, and I'll talk to you on Wednesday.